Hey there, Adrian Rosebrock here from PyImageSearch.com, and today we're going to be talking about building image adversaries using Keras, TensorFlow, and Python. So, image adversaries are a pretty interesting concept, and I think they're best explained visually. So here's an example figure from the blog post. Here we on the left, we have this input image of a panda, and it's been classified by an arbitrary neural network that's been pre-trained on the image in a data set as a panda with 57.7% confidence. Now, our goal with an image adversary is to actually manipulate the decision, the classification of the neural network without it actually without the one without the network knowing, and then two, such that the resulting image is just indistinguishable from the original to the human eye. And we do that by adding in this noise vector here. This isn't a random noise vector. This is purposely constructed during the adversary generation process, and then the output is actually the neural network confuses what the original input image is. So again, here we have input image, which is a panda with 57% confidence. We're going to construct this noise vector, and then the output of which is going to be a misclassified image. The neural network originally thinks it's a panda, but once you add in this noise vector, it turns into a gibbon, which is similar to a monkey or an ape. I think it's a gibbon is actually in the ape species rather than the monkey species. But regardless, that's beside the point. We're going to learn how to build these image adversaries throughout the rest of this tutorial. But if you take a second and just kind of think back on a higher level, like outside of the actual computer science, the computer vision and deep learning aspect of this, you might consider, why are image adversaries a big deal? Why does that actually matter? Well, I have this following figure here that I want to illustrate for you. Let's say it's 20, 30 years from now. All of the normal cars on the road have been replaced. Tesla is the runs a monopoly on the self-driving car business. Every self-driving car, every self-driving truck on the road is a Tesla car. It is ran by Tesla deep learning models that the Tesla engineers have engineered to work very well with high efficiency, low rates of accidents, and they work very well. That's all well and good, but that could run into a problem because if Tesla is using one or two specific models to run their entire fleet of self-driving cars, that could mean that could be a very open vector of attack to someone acting nefarious in the computer vision space. So, for example, let's say you're driving along the road, and along the side of the road on a building, or maybe on the road itself, you see a piece of graffiti. And if you see that piece of graffiti on the road, you can be sure that your self-driving car does. The camera sensors on that self-driving car are picking up that piece of graffiti. So it sees it, but normally it would ignore the classification, right? It would say, well, that's not a pedestrian. That's not another vehicle. That's not a lane switch in progress. That's not someone braking. That's not a standard anything that I should be worried about. But this particular piece of graffiti has been manipulated via a targeted adversarial attack, meaning that the attacker had taken the original piece of graffiti, added in this attack, printed it out, and plastered it on the road. And when they did that, they caused your neural network to misclassify, just like it did here. So while the neural network thought this was a panda, it actually added in a noise vector, and then it resulted in a given classification, which of course is incorrect. The same thing could be applied here in a self-driving car context. You have your input image, you have your noise vector, and once that's output, it causes the neural network inside the self-driving car to misbehave. It may think that a car is trying to swerve in front of you. It may think that there's a stop sign in front of you, or worse, there's a pedestrian trying to cross the street. It slams on the brakes, swerves, takes you into a barrier, and causes a car accident. That is a very real possibility. That's something that deep learning engineers have to consider when developing these models and deploying them out into the wild, because there are nefarious actors out there, and they could potentially use these deep learning models if they have access to them to construct these adversarial images, which could have massive consequences, especially in terms of self-driving car. And this image here does a good job showing showing some of the possible consequences. So here we have a stop sign. This is the original input image. The neural network can correctly classify the stop sign image. We add in this adversarial vector, and then it changes the output of the neural network such that the network thinks it's a yield sign. But to us, these two images right here are essentially indistinguishable. They look the same to the human eye. So that's something that we want to learn how to prevent against. But in order to prevent against it, we actually have to understand how these networks are constructed, or these adversarial attacks are constructed. So at the remainder of this tutorial, you're going to learn a lot about constructing basic adversarial attacks. And in next week's tutorial, we'll go into targeted adversarial attacks and how they work. So I'm actually going to start with the output of this neural network and what we're going to be discussing here, and just show you what we're going to be doing. And then once you understand that, we'll go back and implement all the code to do it. So here on the left is our input image, and it is correctly classified by ResNet with 99.97% accuracy as a hog label. Now, by constructing the adversarial attack in this image, that same ResNet model is going to think the same image is a wombat with 100% accuracy. And for the record, a wombat looks absolutely nothing like a pig. So it's pretty substantial difference, and you're going to learn how to construct this type of attack in this example. So I'm going to open up the project directory structure here. It's fairly simple. We have two Python scripts that generate adversary, which will, as the name suggests, will generate the adversarial attack. The predict normal script, this is used to actually predict the normal class label without any type of adversarial attack. And then inside here, we have inside the PyImageSearch directory, we have our ImageNet class labels and a utilities Python file that will actually go ahead and parse this ImageNet class label file for us. Here is the input pig image that we're going to be working with, and this will be the adversarial image that is constructed by our generate basic adversary.py script. Again, to the human eye, these images are identical. Yes, this one has been resized as a pre or post processing output, but to the human eye, these images are the same. So it's kind of crazy when you think about how we're able to confuse our neural network prediction. So I have PyCharm open here, and I have the project directory structure loaded in, and as you can see, we have our ImageNet class label file, our utilities functions, our generate basic adversary function, which will generate the adversarial image, and then our predict normal script, which will actually take an input image, which is this pig.jpg image, and classify it to demonstrate that our script is behaving as it should and correctly predicting the class label. So let's start here with our PyImageSearch module, and specifically our ImageNet class label index file. The network's pre-trained on ImageNet can recognize 1,000 possible class labels, as we can see here in this file. Here, I'll start at the top here. This is the integer class label index, and then there's a two-tuple value. This JSON file is a dictionary, so we have a list of keys. These are our integer indexes of each class label, and there's a two-tuple value out of here. This is our ImageNet ID for the particular class label, and then this is the human readable class label. So take some time to familiarize yourself with this file. But all you really need to understand here is that this is just a lookup dictionary. So we could pass in the ImageNet class label index and get these two values out. Our utilities file here actually handles parsing the ImageNet class label JSON file. So here we have our inputs, and then we have a function called getClassIndex, which accepts a human readable class label, such as goldfish, and then the goal of this function is to return the integer index. And we do that just by inverting this dictionary. So what we do here is we derive the path to where this ImageNet class label index JSON file lives on disk. We open a file pointer to it, and then we construct a dictionary that maps the label, the human readable label, to the actual integer index right here. So that's all this line of code is doing. It's loading the JSON file, and then it's inverting the dictionary relationship. And then finally, what we're going to do here is now that we have our ImageNet class label dictionary defined, we'll pass in the human readable class label, which will return this integer value. And if we pass in a label that doesn't exist in the dictionary, then we'll return a value of none. So now that our utilities function has been defined, let's implement the predict normal script. So again, this function or this script is going to accept an input image such as this pig, and it's going to classify the label or classify the image, and then also give us the ImageNet integer index of the predicted label, which we'll need once we generate our adversarial attack. So here are our inputs. We have our get class index utility function that we just implemented. We'll be using the ResNet 50 architecture pre-trained on ImageNet. We'll use this function to decode the predictions from the ImageNet network, and then we'll use this function to pre-process our input image. And then we have our IMUtils library, and then our OpenCV bindings. This pre-process image function should look pretty standard to you if you've ever worked with tutorials on PyImageSearch before. This function accepts a single input image, will convert the image from BGR channel ordering to RGB, will pre-process it and scale it using the ResNet specific pre-process input function, resize it to 224 by 224 pixels, and then add in our batch dimension. After that, we return the image to the calling function. So we move down here. These are our command line arguments. We only need a single command line argument, which is the path to the input image on disk. Once we have that command line argument, we'll load the image from disk and make a copy of it so we can draw on it after the image has been classified. So now we're going to move on to pre-processing the input image. We'll resize it such that it fits nicely on our screen. We'll call our pre-processing utility that we defined up here, and then we'll load ResNet from disk, again using weights that have been obtained by training on ImageNet. This line of code here makes predictions on our pre-processed image, and it grabs the top 3 predictions from the ImageNet class labels. That way we could see what the top 3 class labels are. We loop over each of the top 3 labels here. If this is the first, this is the top 1 prediction, we'll call our get class index helper utility and passing in the human readable class name. This will again give us the integer index of what the predicted class label is, and we'll see why that's important once we get into our generate basic adversary script over here. Otherwise, we display the top 3 predictions, including the human readable class label and the probability. And the final step here is we're going to draw the class label prediction and confidence on the output image, and then finally display it to our screen. Let's go ahead and run this script. I'm going to copy and paste the usage up here, throw it into my terminal, and then we'll let the script run. So it's going to load ResNet, going to make a prediction on the input image, and here we could see hog. The input image is classified as hog with 99.9%, 99.97% accuracy. The output here in my terminal is a little messy, so I cleaned it up in a separate text file. But you can see what's going on here. So we load our input image, we make predictions using ResNet, and then we obtain our top 3 class label probabilities. The get class index function here is what is being output here. So for the hog class label, which is the top 1 prediction, we have the ImageNet integer class label index of 341, and you could see that if you pop over here into this file and look up the 341 index, you could see that's the hog label. So we know our script is working correctly there. We know what our ImageNet index is. Now let's move on to our generate basic adversary script. I'm going to open this up here, and then we're going to start with our imports. We have the Atom Optimizer, which we'll be using when we're actually generating the image adversary, the ResNet 50 architecture, which is the same model that we used over here, again pre-trained on ImageNet, our sparse categorical cross entropy function, which is our loss function that we'll be using when generating the image adversary. These 2 functions here are the same from our previous script. The first one is used to decode predictions from ImageNet. The first one is to pre-process images such that they can go through the ResNet 50 network. We have our raw TensorFlow bindings, NumPy, argparse for command line arguments, and then the OpenCV bindings. Let's start with our pre-process image function, very similar to our one in predict normal. We pass in our input image. We'll swap the channel ordering from BGR to RGB. We'll resize it to 224 by 224 pixels, and we'll add in our batch dimension, and then finally return this function, or return the pre-processed image to the calling function. We have this clip epsilon value here, which is going to be very useful when we want to make sure that either image pixel intensities fall within a certain range, whether that's 0 to 1 or 2 or 0 to 255, or when we're constructing our actual gradients, or constructing computing the gradients such that we can construct our adversarial image. This will be a very nice helpful function to ensure that the output image, the output adversarial image here, doesn't look too distorted, because again, we want the output adversarial image to look near identical to the input image as humanly possible. We don't want the human eye at a glance looking at this image to be able to discern, oh wait, this image has been manipulated in some manner. So that's exactly what this clip epsilon function is supposed to do. We input a tensor to it, whether that's an input image or a vector that we're constructing during the adversarial attack process, and we're going to set the min value to be a negative value of epsilon, this argument, and the max value will be a positive value of epsilon. Any value that falls below negative epsilon is set to epsilon, and then any value inside the tensor that is greater than the positive epsilon value, we set it to positive epsilon. So that's our primary utility functions. Our next function, generate adversaries. This is the true workhorse of constructing this basic image adversarial attack. This function accepts our model, which is our ResNet 50 architecture, a base image, which is our input image, which will be this pig image right here. Our delta, which is the noise vector, which if you go back to the example images, this is the delta here is this noise vector that we're going to be constructing. The class index is the ImageNet integer index, which we just found by running our predict normal script. So for the pig image, that is integer index of 341, and then steps are the number of steps we're going to apply for gradient descent. So with that said, we're going to start a for loop here. We're going to loop over our number of steps. We're going to use the gradient tape function to record our gradients, and then the watch function explicitly tracks the delta value as it changes. Again, the delta value is this noise vector that we're going to be constructing. To actually build the adversarial image, it's actually just a basic a vectorized addition process. We take our input image, add that delta vector to it, and then we'll construct the adversary by calling our pre-process input function on this adversary that we constructed by the addition process. So now that we have the adversary, we're going to pass it through our model to actually compute our predictions. And then once we have our predictions, we're going to use them and supply the class index to calculate the loss with respect to the original class index. Because again, our goal is to make the model think that the input image is not a pig, which is why we're taking the negative loss right here. If every 5 steps we'll print out a little status update to our terminal showing what what step number it is, along with what our computed sparse categorical cross entropy loss function value is, and then outside of our with statement here. So this is after we've watched the variable, after we've pre-processed our input image, constructed the adversary, computed the loss, we're actually going to calculate the gradients of the loss with respect to that input noise vector. So doing that yields our gradients. We can apply the gradients to the noise vector, and then we'll clip any values in our noise vector that are falling outside of this epsilon range. And the final step is to return the noise vector to our calling function. That's it for all of our utility functions. Now we can move on to the rest of this driver script, and we'll do that by parsing our command line arguments. This here is the path to our input image, which is our pig.jpg image. The output will be our adversarial.png, the targeted or the adversarial image that we construct in order to confuse ResNet. And then class index here is the ImageNet class label index of the predicted label. So again, this pig.jpg image had an ImageNet integer index of 341, so that'll be the value we pass here. Here we have our a couple training parameters, our epsilon value, which is 2 divided by 255. This is a pretty standard value you'll see in image adversary research. It's used such that the magnitude or the weight of the actual noise vector is significant, but such that once it's applied during this addition process right up here, that it doesn't make the image so distorted that it looks different to the human eye. Because again, the point of these image adversaries is we want the input image to look as we want the our output adversarial image to look as similar to the input image as we possibly can. So this is a pretty standard value you'll see whenever applying adversarial attacks. And then here is our learning rate. This value was tuned empirically through a number of experiments. If you apply this script to your own input image, you may find that you need to tweak this learning rate a little bit. So make sure if the output isn't what you want and the image isn't being misclassified, make sure you tweak this learning rate value a bit. Here we load our input image from disk and pre-process it using our helper function that we defined up here. And then similar to predict normal, we load ResNet pre-trained with ImageNet weights. We'll initialize our Atom optimizer, supplying our learning rate that we defined up here. And then we'll initialize our loss function as well. So in order to construct the adversarial image, we need to allocate some memory inside of TensorFlow. So the first thing we'll do is create a constant for the base image. And the reason this is a constant is because the base image isn't being updated during the gradient descent process up here. So we can just set that as a constant. The delta, on the other hand, that's the noise vector that's being constructed. So that is a variable, and it should have the same spatial dimensions, width, height, and number of channels as the input image. And again, this value will be updated as we go through the gradient descent process. So with our model loaded, our base image constructed, and our delta vector initialized, we can call the generate adversaries function, passing in the ResNet model, the base image, the vector that'll be updated during the gradient descent process, and the class label index of the ImageNet label that we're working with, which again is 341 since this input image is a hog. So this function will run, and then the output will be our final noise vector. So to construct the output adversarial image, we'll add the base image with this delta vector, and we'll clip all the pixel values to the range 0 to 255, and convert the image from a floating point data type to an unsigned 8-bit integer. And then the final step here will be to swap our channel orderings such that we can write it to disk. Because remember here, one of the pre-processing steps was to go from BGR channel ordering to RGB. Here we're doing the inverse. We're going from RGB to BGR, which is how OpenCV represents images. They use the BGR channel ordering, and then the output adversarial image is written to disk, which will be this adversarial.png image right there. So the next step is just to actually verify and demonstrate that the adversarial image here has been incorrectly classified by the neural network. So what we'll do is we'll again construct the adversary by adding the base image and this delta noise vector together. We'll pre-process our this adversary image using the ResNet 50 helper function. We'll make predictions on it, and then we'll show the top three class, or excuse me, we'll decode the predictions for the top three, but only show the top one class label. Again, verifying that our network has incorrectly classified this image. And the final step here is we'll annotate the output image with the incorrect label as well as its corresponding confidence, and then display the output adversarial image to our screen. So let's go ahead and do that. I'm going to go ahead and grab the command line, the script to run in my command line here. We'll load our input image, and then at the same time we're going to load the ResNet 50 model. And then here we're going to start generating this noise vector. Again, this is where the actual the actual adversary attack comes in. So we're applying gradient descent here for each of the number of steps. And even though we have a pig input image, the output is the ResNet model has now confused it as a wombat. So looking at this script though, you're probably thinking, okay, well, what if I didn't want the output image to be a wombat? What if I wanted to be able to control what what the final label is? Is that possible? The answer is yes. It's called a targeted adversarial attack, and that's exactly what we'll be covering in next week's tutorial. By applying a targeted adversarial attack, you'll actually be able to go into the ImageNet um, class label index file and say, oh, I'm going to pick whatever label I want. So I want this pig image to instead be misclassified as a beaver. And then what we'll end up doing here is going back into this generate adversaries function and updating our loss to not only compute this loss here with respect to the original class label, but we'll also compute the loss with respect to the new label that we want the image to be classified as. It's a really simple update, but it requires a bit more explanation. So I'm going to go into that next week. And then in future tutorials on PyImageSearch, if there is enough interest, which I assume there will be, we'll start talking about how we can defend against these adversarial attacks, right? Because this is a pretty serious problem if neural networks can be forced to misclassify an input image just by generating a noise vector. Someone nefarious with access to a deep learning model, specifically the raw weights, and was able to load it in a deep learning library such as Keras or TensorFlow or PyTorch or Caffe or whatever. They'll be able to act nefariously upon it, and we want to be able to protect against that. And in order to do that, there's various training procedures we can use. We can actually generate adversary images and use them as training images. There's neural structured learning. There's all types of different techniques we can apply. So I look forward to covering those topics with you, and I'll see you next week.